So, hello everyone, my name is Serhii. Today I'm going to present you CloudJIT, our just-in-time function as a service optimizer. This is work in progress effort. I would like to start with introduction into function as a service. So function as a service, or FaaS, is a novel cloud computing model for fine-grained computations. In FaaS, applications are designed to be composed of slim functions, and there's an important bit around half of all functions. According to Microsoft Azure Function Study, they execute under 1 second, which means they are very short-lived. And around 70% of all functions, they are called at most every 20 minutes, or less frequent than that, which means they are called very infrequently. In function as a service, you don't have a server that is constantly running your application, your functions. Therefore, resources are allocated on demand, which means that if there is an invocation to some function, but there is no available function worker for that invocation, then a call start happens. Also, in function as a service, it is the responsibility of cloud service providers to provide computing infrastructure for running functions, which not only makes it easier for cloud customers to deploy their applications, but also provides cloud service providers with a more substantial amount of control over computational resources, and it allows cloud service providers to employ some optimizations. So functions are mostly written in high-level languages. According to another study, these languages execute atop a managed runtime, and managed runtimes are usually heavyweight processes which leave a significant memory footprint, ranging from tens to even hundreds of megabytes. They take some time to load and initialize before they become actually available to run the actual code. It can take tens of milliseconds, and if a managed runtime features a just-in-time compiler, then it is also subject to warmup. And therefore, traditional language runtimes, they were designed and they fit for long-running applications such as servers. However, we claim that FaaS is not the case for it. So here we can see a structure of a call start. At first, we need to initialize a function worker, which can be a VM or a container. Then we need to download the code inside this worker. Then we initialize the language runtime, run the function initializer. These are all parts of a call start, which can take up to several seconds. And only after that, we actually start executing the actual function code, which, as we saw before, usually takes less than 1 second on average. Therefore, we claim that frequent and slow call starts can take up a significant fraction of the overall execution time. And in our project, we are mainly focusing on improving these parts of the call start that relate to language runtimes. So, a possible solution to fight slow call starts is to employ an ahead-of-time compilation. With AOT, all code is compiled into standalone native binaries beforehand, before execution. No interpreter nor JIT is needed, just a slim runtime that doesn't pay a price for the features it is not going to use. And no profiling and just-in-time compilation is involved. And all this in combination results in faster startup, lower memory footprint, and immediate peak performance. Also, such ahead-of-time compilers as, for example, GraalVM native image, they also run static initializers for classes during compile time, so they are not always executed at the beginning. We executed a couple of micro benchmarks based on 3 Java applications written in popular microservice frameworks. On the left plot, we can see the improvements in the footprint, and on the right plot, we can see more substantial improvements in startup latency. We used GraalVM native image to ahead-of-time compile our applications, and we compare it against traditional JVM. So another good thing about GraalVM native image is that it's a trending technology, which is being widely adopted in production, as we can see from these tweets. It improves execution performance. It makes it easier to compile Spring Boot applications. Another example of production adoption of GraalVM and integration of GraalVM into Spring Boot. However, ahead-of-time compilation comes at a price. Ahead-of-time compilation itself is a very resource-consuming task that can take up to several minutes even for simpler applications, and it imposes high CPU and memory utilization. Also, ahead-of-time compilers, they usually operate under closed-world assumption, which means that only those components that are known at compile time will be included in a final image. Therefore, only those components will be available at runtime, which limits use of some of the dynamic features, such as, for example, reflection or serialization in Java. So we claim that ahead of time applying ahead of time compilation to blindly compile all the functions is not a solution. Coming back to function as a service, again, the same study from Azure Functions. We highlighted some functions on the left plot. The left plot shows us how many functions are actually being executed at each point of time. And on the right, we can see how many call starts happen. So we can see the highlighted, or as we mark them, optimized functions. There is a minority of these functions, but they generate a vast majority of all call starts. So having this in mind, we introduced CloudJIT. CloudJIT is a function as a service platform that features a just-in-time optimizer. As its name suggests, it is inspired by traditional JIT compilers. Traditional JIT compilers aim at compiling methods or other code snippets. CloudJIT compiles entire FaaS functions. JIT compilers, traditional JIT compilers, they do not aim to actually compile all the functions, all the methods or code snippets. They identify hot paths, hot methods that are executed frequently. It means that they're going to benefit from it the most. So does the CloudJIT. It identifies popular functions that experience the most call starts and compiles only this selection of functions. So ahead-of-time compilation in CloudJIT is performed by GraalVM native image, but it is only applied to a limited subset of functions, as we discussed. And the key component of CloudJIT is an optimizing pipeline. So here is how it looks like. The first stage is a HotSpot with agent. So this is traditional JVM that features a native image agent. This agent is needed to collect agent configuration to enable use of some of the dynamic features, such as reflection. Then the next stage is just a traditional JVM. If the function never gets picked up for compilation, for optimization, then it's going to be the final state of this function. Otherwise, if the function gets picked up for compilation, then a parallel process called native image builder is being spawned for this function, which results in a standalone native image binary. And then the function goes to the final state, which is a native image. In case the function cannot fulfill some request due to, again, closed world assumption limitation, it was not configured properly, then it comes back to the first stage and the entire pipeline is repeated for that function. So we ran an execution evaluation on the same trace as we saw before. But we downscaled this trace to accommodate its load in a single cluster node. And the results show that we compiled 27% of the functions. And it resulted in 30% on average of call starts optimized. And also memory utilization got reduced by 30% due to ahead-of-time compilation. So the bottom line is we propose using ahead-of-time compilation only for some functions in function as a service model. We propose a platform, CloudJIT, that prioritizes certain functions and selects them for ahead-of-time compilation. And we demonstrate the feasibility of such an approach in a realistic function as a service environment. For the future work, we plan to incorporate profile-guided optimizations for native binaries to improve peak throughput so that the compiler would be able to feature more aggressive optimizations. And we plan to incorporate checkpointed execution based on snapshots to further improve call starts. So that's it. Thank you very much for attention, and see you at the poster session.
Do we have questions or observations from the audience gathered? I come with one. So if you could flip back to your previous statistics, it had about 30% improvement.
Yes.
So I was a little surprised there in a way, because often we see things where you optimize, say, about a third of things. You get about 2/3 of the performance benefit. So do you have any insight into why this was more just 1/3 and 1/3 instead of 1/3 optimized and 2/3 the benefit?
Yeah, the problem with this particular execution evaluation is that CloudJIT is still a prototype. It's still a work in progress effort. And we only were able to execute the workload on a single cluster node. And therefore, we had to accommodate the trace to be able to run it in a single cluster node. Therefore, we had to downscale the trace. And therefore, the invocation patterns for many functions, they got simply lost, which means most of the call starts, they were erased by this downscale process. So in this case, we have just a localized view of a single cluster node. But in the future, we plan to run a bigger evaluation.
Right. So in essence, you believe you weren't able to gather enough statistics to drive the optimization in the way that would be most effective.
Yes, it's not only about statistics, but also about the nature of function as a service itself, as we can see on these plots. So from here, we see that also by optimizing just a small, this is a simulation, by optimizing a small selection of functions, we can get a vast majority of call starts optimized. Therefore, it's not only about the platform, but also about the nature of FaaS invocations.
So I know that it is still a prototype, but how easy would it be to incorporate your tool into my existing functions as a service? Because often it is very important to make things easy to use. So what would I have to do to use your optimization technique with my functions?
So basically, as I said, the main component of CloudJIT is this pipeline, which means when you you can keep your original JVM execution environment, and just when you'll have to incorporate some type of heuristics to be able to obtain this selection of functions that are worthy of compilation. And you'll have to basically put this native image builder intermediate process and then you'll just replacing the runtime for your function from JVM to this native image.
Okay, thank you very much. Would Matthew Parkinson identify himself for our next session speakers? There he is. Okay, so you can find Matthew. He's your session chair for the next session, which will begin at 11. Let's thank our speakers again.